Conceptual Introduction to Linear Regression, Part 4, Example R output. With some hypothetical data, let's look at a simple regression model summary in R. This is the R statistical computing environment, not the letter R representing a correlation. Imagine I set up a simple experiment where people get 0 to 120 minutes to practice a certain kind of math problem, and then I test them and give them a percentage score on the test. So the predictor variable is going to be minutes of practice, randomly assigned, ranging continuously from 0 to 120, and the response variable is going to be the math test percentage score. For this illustration, I made some fake data consistent with this hypothetical experiment. The code is shown here in case you're curious, but you don't need to worry about it for now. Here's a scatter plot showing the relationship between minutes of practice and math test scores. Recall from last week that the function abline adds a line to a plot. So here is the regression line, showing that the relationship is positive. But this is just a visualization. How do we get the values of the slope and the intercept, and the hypothesis tests of those values? We'll use the linear regression function LM, like in the example from last week. We'll practice this more in the future, a lot more, so there's no need to dwell on the code right now. I just want to focus on the interpretation. So here is the regression output that you will get from R. The intercept is 49. What does that mean? It's the expected score for someone with 0 minutes of practice on this math test. Here's that plot again. You can see that the blue line hits the y-axis at around 49. The slope for practice is 0.11. What does that mean? It's how many more percentage points on the math test went along with each extra minute of practice, on average. This is usually the thing we care about the most. We want to know if our variables are associated, and this slope quantifies the association. 1 minute of practice tended to increase test scores by 0.11. And I'm saying increase here because this hypothetical scenario I concocted was an experiment, so there would be evidence for causality. But if we were working with correlational data, then I would want to avoid language that implies causality. This is the p-value associated with that slope. It assumes that you would like to compare the slope to 0 to see if the slope is significantly greater or less than 0. If we were completely randomly picking math scores to go with each amount of practice, the slope would average out to 0 in the long run, but we would need an infinite sample size to get it perfect. For any actual sample we get, the slope would be maybe a little bit positive, maybe a little bit negative, but usually close to 0. This p-value is the probability that a random slope like that would end up being 0.11 or farther from 0. For a sample like ours, if there was actually no systematic relationship between practice and math scores. In other words, it's the probability of getting a slope as extreme as ours or more extreme, with a sample size of 100, if the null hypothesis was true. The p-value is shown in scientific notation here because it is very small. But this just means 5.87 times 10 to the negative 5th power, which is the same as 0.0000587. The probability of getting a slope this big, due to random chance, if practice and math scores were uncorrelated, would be very small. So a fluke is not a very compelling explanation for the result of our experiment, and we say that the slope is statistically significant. How did we get this p-value? Well, it's based on a t-test comparing the observed slope to a null value of 0. The slope comes with a standard error. That is the estimated standard deviation of the sampling distribution of the slope. In other words, if you were to imagine all the possible slopes you could have gotten with experiments like this, they would have some distribution, and that distribution would have a standard deviation, and that standard deviation is the thing that we're estimating here. The slope divided by its standard error is an estimate of how many standard deviations away from 0 our slope would be, if we're continuing to imagine that universe of possible slopes we could have gotten from alternative iterations of our experiment in a world where the null hypothesis is true. This slope divided by standard error is the t-value, so called because it has a t-distribution with 98 degrees of freedom as long as certain assumptions are met. Once we know a t-value in degrees of freedom, we can use the known shape of the t-distribution to get the p-value. That's what the computer did here. The p-value is the area under the red part of the curve, the t-distribution shown, the probability of randomly getting a t-statistic more extreme than 4.2. It is very unlikely to get a t-statistic this extreme just by rolling the metaphorical unweighted dice in a world where practice is unrelated to math scores. That's why we argue that it makes much more sense to say we're dealing with metaphorical weighted dice, that these variables are not just totally independent and random. Instead, practice is probably systematically helping people do better on the math test, or at least plausibly systematically helping people do better on the math test. So why 98 degrees of freedom for this t-distribution? Well, there were 100 participants, and we estimated two parameters, an intercept and one slope. 100 minus 2 is 98. R squared is 0.15. What does that mean? 15% of the variance in scores was accounted for by practice. Don't forget the adjusted R squared if you have a complex model. It's a bit lower than R squared to account for the fact that adding any predictor is almost guaranteed to bring the regular R squared down, even if the predictor is useless. And the f-test at the bottom of the output tests whether the model as a whole performs significantly better than just guessing the mean for everybody's math test score. In this case, we have only one predictor. So testing whether the model as a whole performs significantly better than just guessing the mean is the same thing as testing whether our individual predictor is statistically significant. You can see that the p-value of those two tests is the same. But when you have multiple predictors, this won't be the case. Most of the time, we don't care about this f-test. It's not that useful to test all the predictors together, the model as a whole. In models with many predictors, it will almost always be statistically significant, because it is very easy to perform better than just guessing the mean for everyone. But performing significantly better than just guessing the mean for everyone for our entire model doesn't really tell us much about the things that we tend to want to know as psychologists about our experiments. It is much more useful to test the slopes of the individual predictors. So the most important part of the output is the table of slopes, and most of the time I will focus on this part of the output. Sometimes I may even only show this part of the output. One more very useful piece of information, as important as the things in the table of slopes, but not displayed there automatically, is confidence intervals for those slopes. And you can get these using the confint function. It will give you a confidence interval for each slope. This is a 95% confidence interval by default, but you can change that by adding an additional argument to confint if you want to.